Hi-oh, here we are. Current and magnetic fields. Turns out there is a connection between the two of them. In fact, you can't have one without the other. Anytime that you produce a current, a magnetic field is produced. Think about that for a moment. This was an amazing discovery. Before, it was thought they were completely separate things. But now we realize magnetism is the current, like ice is the water. They're really the same thing. They're just different forms of it. We have this thing called the right-hand rule. So remember, I've had students mess this up because they end up using their left hand because they're left-handed, and that's okay. But you have to realize you must use your right hand. Take a look at the picture of our hand here. Your thumb goes in the direction of the current, and your fingers show you the direction of the magnetic field. Remember, outside of a magnet, it goes from north to south. So we can determine the direction of the magnetic field based on the direction that we send current through a wire, or vice versa. If we know the direction of the magnetic field, we can determine the direction of the current. So take a look at this picture. Take your right hand and pretend you're holding on to the wire. Put your fingers so they are spiraling around the wire. Remember, use your right hand, and your thumb will point in the direction of the current. And which way does the current flow? Well, to the left, of course. Often, because we're working on two-dimensional pieces of paper, we have to be able to show 3 dimensions. So a notation has been used, an X to represent the field is moving away from you, and an O to represent the field coming out towards you. So this particular picture, it's coming out over here, and it's spiraling out of the page and going in here. And so we can use the right-hand rule and figure out which way the current is flowing using this notation. So take your hand, your right hand, and make it so that your fingers are going into the screen on the top, or coming out of the screen when they're at the bottom or below the line, the wire. And of course you'll find your thumb is pointing to, well, wait a minute, yeah, that's not right. To the left it should be. Thumb is pointing to the left. And so the current's flowing to the left. If you keep this notation and you make a loop with the wire, what you find is your fingers bunched together, or all those magnetic field lines bunched together inside that loop. So we make an extremely long or strong magnetic field inside a loop. And we can use this to our advantage. We can produce what's called a solenoid, and a solenoid is nothing more than a coil of wire that when we run current through it, it acts as a magnet. If we add an iron bar to it, and that iron bar helps to intensify the field and direct the field, much like plumbing does for water, we have what's called an electromagnet. So an electromagnet is nothing more than a solenoid with an iron core. So how do these magnetic forces affect charged particles? Well, believe it or not, there is a relationship here. And the way you can think about it is, with my little skateboarder person, if there were grooves in the pavement here, and that's signified by these arrows, and the skateboarder is just standing there, they're not moving over them, the skateboarder doesn't feel the grooves, doesn't feel the force of the grooves affecting them. So there's no magnetic field produced by a charge that's not moving, and therefore no forces. What happens if our skateboarder moves parallel to those grooves or parallel to the field. They're not going to encounter those grooves at all. They're not going to bump over them, and they won't feel a force. But what if the skateboarder goes across them, perpendicular? It's going to feel every bump in the road. It feels a force. So similar to our skateboarder, charged particles have similar experiences. Instead of grooves, we're talking magnetic fields. You can see. So let's put this into practice. Science is nice, but when we can make technology with it, it's awesome. The old-time tube televisions. Basically, you had magnets all around the tube. And when you would send a charged particle or an electron through that magnetic field, by turning those magnetic fields on and off, you could cause the electron to deflect, and you could control exactly where it was going to fall on the screen and make the screen glow in that location. Similarly, we can describe the aurora, how that happens. If we have the Earth and we have the magnetic field coming off the Earth, the charged particle is coming in perpendicular, it's going to feel a force and deflect away. But if the charged particle is coming in near the poles, notice it's coming in parallel, it's not deflected, it hits our atmosphere and causes it to glow through something called triboluminescence.